Okay, capacitor charging, discharging functions. This is where we just look at the curves you've already learned all about, and we'll just put a name, well, we'll just put the formula there for the actual function. You all know the circuit where we've got a battery, and it goes up through a lamp, if you like, or a resistor, and we've got a capacitor, and it gets charged up. Obviously to the same voltage that, well, eventually the same voltage, or just about, that the EMF source had. So that's the circuit we have for a charging circuit, and you know by now that the one graph that you need to remember out of all the 8 graphs you will eventually learn is this one. It's the voltage against time for the charging of the capacitor. The voltage on the capacitor takes time to build up. You've got to have that transfer electrons. Starts off quite fast, but slows down, and that's because obviously when it starts off there's no charge on it. The energy difference is much bigger. What you probably haven't got is the equation for this charging, and it's easy enough to figure out. All you do is you write a little Kirchhoff's equation for the circuit. It's your EMF, so positive going that way, and you put your resistor in, you put your capacitor in. Your capacitor is in terms of volts. You just write in the voltage formula for the capacitor, and then you can solve that equation, and you can solve it in terms of charge. Once you've done that, you can get the current. Once you've done that, you can get the voltage, and that will give you the formula for that curve. And I won't go through all that, although we can. It's a function of t, obviously, and this is the one that's a little bit trickier. But we start off with our EMF source, so we'll call that E. 1 minus E to the minus T over RC. And that's the formula for the charging. Now, I'll quickly do the formula for the discharge circuit. Remember, that's I against T. Remembering that eventually, sorry, I jump around a bit, the voltage on the capacitor is going to come up to the voltage that was on that EMF source. The current starts as if there's no capacitor there. So the current starts off at a maximum of the EMF source. So the maximum here is the EMF source over the resistance, which is the maximum current, which I sometimes call I0. So that was an E. It's a bit crappy because I've got a crappy pen. So what's the formula going to be for this one? The formula for this one's even simpler. It's going to be I as a function of t is going to be that initial current that we had, which I've said is E over R, which we could call I0, E to the minus T over RC. Now, these formulas here we need to know for some problems that we're going to solve. And when you've got these formulas, you can actually see where the 0.37 comes from for this graph, and the 0.63 comes for that graph for the time constant being RC. And you can also see where that time constant came from with these equations. If we look at these equations, we'll see when t equals the RC, we get e to the minus 1. E to the minus 1 is 1 over e. E is 2.7, or about 2.7, so 1 over 2.7 equals 0.37. So you see where you get the 0.37. When t equals 2 time constants, then we've got e to the minus 2, which is 1 over e squared, which is 1 over 2.7 squared. So you're starting to see where you get that 0.37 squared. This one, however, has got the E, or the maximum voltage, times 1 minus that. So the whole thing becomes 1 minus 0.37 for one time constant, or 1 minus 0.37 squared for 2 time constants. But this formula we're going to use if we need to solve some more tricky problems. Now, the discharge curves both go like this. Now, voltage against time, current against time. Now, the current against time graph should actually be around the other way, because obviously when you discharge, the current runs opposite to the way it did when it was charging. But it's normally shown this way, so we will continue to do that. We'll continue to show it that way. Now, when you see the graph looking like that or like that, you know it's going to have a formula that's similar to that. So the formula for the charging, or the discharging, sorry, for I against T is again just the initial current, I naught if you like, e to the minus T over RC. I naught being whatever that voltage is on the capacitor if you like, and the resistance in the circuit or the lamp. The voltage one, let's have a think about that one. Yeah, the voltage one's going to be also pretty similar. We'll just do that one as a, well, it's going to be V as a function of T is going to be equal to Q over C, which is the voltage on the capacitor. I'll write it that way just so that you get used to seeing things like that, minus T over RC. The I naught here we could have written also as Q over RC, right? Q over RC, but we wrote it down as that. Current being the voltage divided by the resistance, the voltage on the capacitor divided by the resistance, the voltage being charge over capacitance. So we could have written that one also as Q over RC. So these equations, need to know them. They'll be helpful for some problems.